the ability to isolate layers that are one atom thick have changed the way that we think about materials. Because all the atoms are accessible at the surface, we can now change the properties of a material, we can change the electronic properties without changing the chemical composition. So what I'm going to tell you today is about two such examples. One, and both actually involve graphene, which is a one atom thick crystal of carbon. And in both cases, what we're going to be after is so-called flat bands. Now, flat bands is a case where the kinetic energy of the electrons is quenched, and as a result, the interactions between them become important, and they're able to create coherent macroscopic state where they move in lockstep and give rise to interesting phenomena such as superconductivity, charge density wave magnetism, and so on. So the way we're going to try to change the band structure of this material is to induce flat bands and to see what happens. So the two systems that I'm going to talk about is one where we stack two graphene layers on top of each other with a twist between them and see what happens. Eventually we get to a completely flat band. Another strategy is where we take a membrane of graphene and we allow it to buckle out of plane, and there's very interesting pseudo-magnetic field, something that actually mimics a magnetic field as far as the electrons are concerned and gives rise to pseudo-Landau levels where the levels are flat. So let's get started. The other day, when I went online to buy graphene for my lab, I ran into this ad here that of a company that manufactures graphene. And what they're saying, the argument of this ad is that the tradition of naming epochs in human civilization by the materials that were used underlies their importance to our everyday life, for making tools, making weapons, for communications, for transport. So they go through all the epochs of human civilization: stone, bronze, iron, steel, silicon age, and they get to carbon age. Now, in view of what happened the last 15 years, their enthusiasm is maybe not unjustified, because since graphene was first discovered in 2004, it has amassed a long list of superlatives: strongest material ever measured, stiffest known material, highest intrinsic mobility, highest thermal conductivity, and so on and so forth. On the other hand, it has also given us many surprises in terms of electronic properties, including ballistic transport, fractional quantum Hall effect, orbital magnetism, and most recently, superconductivity. However, I would argue that the revolution is not really, it's not due to carbon itself. What matters here is the fact that it's two-dimensional. It's the dimensionality of these layers. And since 2004, many new two-dimensional materials were isolated with various interesting properties: semiconductors, insulators, topological insulators, superconductors, magnets. By now, there are several dozens of these two-dimensional materials that people probe and study in the lab, and they actually try to make useful devices out of. In fact, there were a few thousands other materials that have not been realized yet, that were predicted theoretically, predicted actually through a computer. So two-dimensional materials are beginning to be a very rich and active area of research, and pretty soon we're probably going to start seeing them coming to market. Now, this is actually quite surprising in view of of this paper here. This was a very influential paper by David Merbit and Herbert Wagner in the 60s that argued that long-range fluctuations can be in two-dimensional or one-dimensional material. Fluctuations are very cheap energetically, and as a result, they are favored because they increase the entropy. So as a result, what they argued, or they seem to have argued, that there's really no long-range order in dimensions less than 3, and in particular, people believe that one cannot have two-dimensional magnets, no superfluids, no superconductors, and no two-dimensional crystals. So these papers and many theoretical papers that followed in the late 1900s have actually put a damper on research in this area and discouraged many people for getting into two-dimensional materials, but because there was always pushback based on this theory here. And in fact, if you actually try to understand what's going on, here is a oops. Okay, let me just go back to, sorry, my, okay, sorry here. Okay, so what we have here is a box in which you throw in 400 carbon atoms and you digitally heat them up to 2000 Kelvin and you watch what happens. And what you see is going on, they fluctuate, they have very large fluctuations due to the temperature, and sometimes they will form what's called a buckyball here, they form rings. But no matter how long you'll be waiting, you cannot form a two-dimensional crystal. And that is because the fluctuations are so cheap, it never gets to form a sheet. So, so can we have two-dimensional materials? So in the early 2000s, Andrei and Kostya Novoselov asked, okay, so the theories tell us that we can't have two-dimensional material, but is there a way to cheat nature and to get there anyway? Because we know that two-dimensional materials like graphite do exist, and mica, another example. So these materials have strong covalent interlayer bonds, so they're very strong in plane, but they have weak bonding between layers. So the idea that they thought of, okay, let's do something like a conjurer's trick, and so imagine that these layers are a deck of cards and just pull out one of these layers. So they went with this idea and they did the following thing. They took graphite, they took a piece of Scotch tape, picked it up with a piece of Scotch tape, and then brought the Scotch tape together and open it up. So you have two pieces, repeat the process many, many times. So you end up with 4, 16, 32, and so forth. And you end up with these many very thin flakes, which next you can take and look at under the microscope. You put it on a substrate here. This is a silicon wafer. And by the faintness of the shadow, you can identify a monolayer or a bilayer or more layers. So, and then you can actually go and measure it with the atomic force microscope and realize that you indeed have a 1 atom thick layer of graphite. Now, this discovery was completely serendipitous. And the reason they actually stumbled on it, I mean, normally you cannot expect to see with even the most powerful microscope, you cannot expect to see a 1 atom thick layer. But what happened, it so happened that they had these obsolete silicon wafer lying on the shelf. These are silicon wafers that were manufactured in the 80s. And they are, if you have ever seen them, they're very shiny. The reason being that they were designed for optical inspection of defects and specks of dust. So what we have here is a constructive interference between light that reflects from the bottom layer, the silicon dioxide interface, and the light that reflects from the top layer. And if you have the right thickness and the right frequency, there are points of constructive interference. So for in this particular case, the wafers were about 300 the silicon dioxide was about 300 nanometer thick, and it was designed to have constructive interference for green light. That is the frequency that our eyes are most sensitive at. Now, if you have a speck of dust falling on it, you go to the constructive interference is destroyed, and that gives rise to this shadow. So in 2004, they tried to publish this paper, and if you listen to Andrei Nobel lecture, he will tell you that it was very difficult to publish this paper because people just simply did not believe them. As one of the referees actually implied that he was faking the data. But they persisted and invited everybody to their lab to show them that, in fact, this is how we do it. And this is how the whole field started. So let me tell you a little bit about flat bands and why are we interested in flat bands and how to get there. So I have to start with an introduction, which is basically the band structure of solids. This is a standard model of condensed matter physics. So imagine that you bring together a bunch of atoms and you make a nice crystal, and each of these ions presents a potential to the electrons that move in this crystal. As a result, every atomic level broadens into a band. Each band can hold as many states, has as many available states as there are atoms in your crystal, in your sample. And the width of this band is determined by the kinetic energy of this electron, which is determined by the tunneling between adjacent atoms. Now, there is something very special that happens when you have a so-called Bravais lattice. A Bravais lattice is one where every atom lives exactly in the same neighborhood as every other atom. And if that is the case, the electronic wave function is basically a modified plane wave. So basically, the electrons can move freely through this crystal without scattering of, practically no scattering of the atoms, as long as their wavelength is longer than the interatomic length. So in other words, as long as the wave vector lives in this what we call Brillouin zone. And in that case, the energy momentum relation of this electron is simply parabolic. Now, just comparing it to classical particles, we can rename the prefactor here of the parabola as an effective mass. So essentially, you see that this particle are free particles that can just zip through the crystal without practically being inhibited. Now what you can do is throw in your electrons and you keep throwing them up. Every state here can take up 2 electrons, one for spin up and spin down. And when you run out of electron, you reach what we call the Fermi energy that separates empty from full states. And the Fermi momentum is, again, the momentum of the highest energy electron. But however, this is not the whole story. There's another energy scale in the system, and that's the interaction between atoms. So how much does it cost to have 2 electrons occupy the same potential here? And that gives you 2 energy scales that compete. So in one limit, when your interaction energy is much smaller than the bandwidth here, we have basically a free electron model. In the other limit, where the interaction energy is much larger than the bandwidth, sorry, this should be a larger here, what we get is a quench kinetic energy, and the electrons can band together and form a correlated state that is macroscopic and where all the electrons move in step. And the band structure changes here. You open a gap. And this is, for example, can be a superconducting state or other kind of correlated state. So here is an example of a few possible correlated states that we can have in a flat band once the kinetic energy is quenched. And you can understand intuitively why that happens. The velocity, the electrons slow down, they come down to an almost stop, and then they can start seeing each other and pair up to decrease their total energy. And the kinds of states that we can have are ferromagnetism, insulators, charge density wave, fractional quantum Hall effect, and superconductivity. Now, when we talk about superconductivity, there were some very interesting predictions that was started with the Finnish group back in the 90s and more recently in 2000 by this paper by Volovic, who claimed that in fact, if you have a flat band, and he was actually talking about graphite, it would be possible to reach room temperature superconductivity. So that gave impetus to many researchers to start looking for flat bands. So how can we make a flat band? Let's start from a regular parabolic band here in a crystal. Here we have the lattice spacing. And in one way to flatten the band, and that's a very simple way, is to put your crystal in a periodic potential whose period is much larger than the atomic spacing. And what happens then, you break up the Brillouin zone into pieces. So each one of these super periods becomes like an atom, and whenever the wavelength reaches the size of this super period, you get strong scattering. So basically, your band structure will have shrunk here and you'd have opened a gap at the new mini Brillouin zone. So now instead of putting n electrons in that to fill a band, now you're going to fill the band with n times the ratio of the lattice spacing to the super period to some power depending on the dimensionality. Square, for example, if you're in 2 dimensions. So here is a very simple recipe to make flat bands. So how can we realize that? So let's go to graphene. What is graphene? Graphene is a 1 atom thick crystal of sp2 carbon. So every core, you have a honeycomb structure here. This is a scanning tunneling electron microscope picture of an actual graphene layer. At every corner here of the hexagon, you have a carbon atom sitting. And in this diagram here, I colored the atoms by red and blue just to highlight the fact that this is not a Bravais lattice. Now notice, remember, Bravais lattice, every atom has to have the same environment around it. However, if you look at the red atoms, which we call A, they have a blue neighbor north, but no neighbor south, whereas the blue atoms have a neighbor south, but no neighbor north. So clearly this is not a Bravais lattice. And the story that I told you about block wave functions that are basically free electrons moving in a lattice really will not work here. So what happens? So let's go back to when you have a simple metal like copper or gold, you have a parabolic band structure, and the electrons move as if they were free electrons with some effective mass. However, in the case of graphene, because this is not a Bravais lattice, you get strong diffraction from the lattice, and the band structure looks nothing like this beautiful parabola. It actually looks like this. This was already solved back in 1947 by Wallace. And let's see what the consequences of such band structure are. So first of all, what are the ingredients that went into this band structure? There are basically three ingredients. The fact that the material is two-dimensional, the fact that it's a honeycomb structure, and the fact that you have identical atoms on the two sublattices A and B, they're both carbon, and also that you have identical hoppings between any atom and its near neighbors. So that gives you this band structure here. Notice that nowhere in these ingredients, which are necessary and sufficient, did I mention that this has to be carbon. In fact, it doesn't have to be carbon. People have managed to get the band structure of graph, the same band structure with all the elements on the fourth column of the periodic table. You can engineer these conditions in the microwave cavities. People have done it by organizing atoms in honeycomb, molecules in a honeycomb structure, cold atoms, and so on and so forth. So this is quite universal, and it's really only a geometrical band structure. So let's zoom in at low energy. The band structure looks like this. It consists of two cones whose apices, and the blue here is the hole sector, red is the electron sector. Notice the dispersion now, instead of being parabolic, is linear, which is the dispersion that you have in photons or neutrinos. So these are basically the electrons in graphene move like ultra-relativistic particles. They are chiral, and each state now is fourfold degenerate, 2 times for spin and 2 for valley. These two cones, which are not identical, are related by time reversal symmetry. The Fermi energy sits right here, and this is our hexagonal Brillouin zone. So these two cones, we call them K and K prime. So we call them valid. So this is more for the experts. The dynamics of the electrons in this system is determined by this fairly simple Dirac-Weil Hamiltonian, where sigma here is a Pauli matrix that operates now not on spin, but on the sublattice degree of freedom, on A or B, and P is the momentum relative to these K points here. Now, the velocity of these ultra-relativistic electrons is about 1/300th of the speed of light. Now, sigma dot P is basically the chirality operator, and you see right away that these K and K prime are chiral particles, but they have opposite chirality. One is goes clockwise, the other one goes anti-clockwise. So there are very interesting properties resulting from that, which I will not go into. Now, this conical band structure gives rise to linear density of states, or the number of states that are available per unit energy vanishes here at the Dirac point. And that is crucial for the properties of graphene, because it's very easy to move the Fermi energy in this within this band structure. It takes very few electrons to move the Fermi energy, and here I'm going to give you an example. Let's make this is a standard device where you slap a piece of graphene on a silicon wafer. You have a 300 nanometer of silicon dioxide here. You have source and drain electrodes, and then you apply a gate voltage. So just due to capacitance, you are changing the number of electrons in the system, just capacitively. And let's watch what happens. So I have positive gate voltage. My Fermi energy moves into the electron sector. Negative gate voltage moves my Fermi energy into the whole sector. Notice that I'm doing that without changing the chemistry. In three-dimensional materials, you'd have to change the constituents in order to do this. And you see that 1 volt of gate voltage buys me about 10 to the 11th carriers per centimeter square, or it changes the Fermi energy by 80 millivolts. So now you see, right? So you see immediately we can change the properties just with a simple gate voltage. Another thing that we can do is apply a magnetic field. And what the magnetic field does, it breaks up the band structure into these so-called Landau levels, or the density of state here now, instead of being this linear dependence, constitutes of these, is made up of these peaks corresponding to each Landau level. And the magnetic field is generated by a vector potential, which basically, this is the same Hamiltonian that I showed you before, but it basically shifts the momentum by an amount of the vector potential here. The Landau levels here, you can see the energy levels are spaced, the spacing between the energy level, because of this conical dispersion, are spaced like the square root of magnetic field times the index of the Landau levels here. And so you might say, okay, here you go, you have your flat bands. All you need to do is apply a magnetic field. The problem is that these flat bands require to have a magnetic field, and that is inimical to superconductivity. Superconductivity and magnetic fields don't like to coexist. So we would like to find ways of creating flat bands without breaking time reversal symmetry, or without having to apply a magnetic field. So, one way of doing that is to use strain. So here, for example, I have a blister, let's say in graphene, where I'm pushing up the, where I'm creating strain, and as a result, the lattice, the graphene lattice, become distorted. It becomes strain, and the hopping, which were previously identical, hopping between nearest neighbors, which were previously identical, have now changed. And as a result, the effect of that is to introduce a vector potential, which looks very much like the vector potential that gives rise to a magnetic field. However, notice that there's a big difference. Here we're not breaking time reversal symmetry. So the vector potential in the K, at the K valley, has opposite sign to the vector potential in the K prime valley. In other words, they have opposite we call them pseudomagnetic field in the two valleys. So this magnetic field points up in one valley and it points down in the other valley. So there's no net flux, magnetic flux in this system. And this is just for the expert, the pseudo vector potential is a direct function of the strain tensor in the system. So what you will get is, let's say, a pseudo magnetic field pointing up at the apex of this blister, and the pseudo magnetic field pointing down around it. So because you must have a zero net magnetic flux in the system. So here we have a recipe of creating flat bands that look like Landau levels, but they are created by strain rather than an external magnetic field. So now, since you have a pseudomagnetic field, you're going to create Landau level. We call them pseudo Landau level. But the Landau levels and the density of state, they don't care about the direction of the magnetic field. They are the same regardless of which way the magnetic field points, as long as it is perpendicular to the two-dimensional layer. So we're going to have a pseudomagnetic field pointing up in the K valley and pointing down in the K prime valley. The spacing between the energy level is exactly the same as you would have in a real magnetic field. And the Landau levels that you'd measure by measuring, for example, in a scanning tunneling microscope, the spacing will be the same. So in principle, you couldn't tell the difference. Now, there's something very special about the n equals 0 level here that sits at the Dirac point. And what happens, it has this a so-called sublattice polarization. What do I mean by that? And this is true whether you apply a real magnetic field or a pseudomagnetic field. What I mean by that is the wave function in the K valley sits uniquely on the red sublattice, on the A sublattice, and the wave function in the K prime valley sits uniquely on the K prime sublattice. Now, if you have a real magnetic field, this would be an effect that is completely undetectable. But with pseudomagnetic field, as we will see in a moment, if you can't separate positive and negative pseudomagnetic field, you can actually see, in one case, you can only see the red sublattice being populated, and in the other case, only the blue sublattice populated. And that's what we'll tell you when we're doing, when we're looking at scanning tunneling microscope, the wave function with scanning tunneling microscope will tell us whether or not we have a pseudomagnetic field. So basically so we have now an idea of recipes of how to change the band structure. You can impose an external potential, for example, by putting your graphene on a substrate or any other two-dimensional material. You can impose strain. So you relax the condition of equal hopping parameter by using strain. Of course, there are other ways of doing it, introducing point defect by plucking out atoms from the lattice, applying electrostatic potential, magnetic field. I will focus on the first two. Okay. So twisted bilayer graphene. This is our first. So what I've done here, I've taken a layer of graphene, the green one, I put it down, and I put a red one on top and twisted it. And as you twist it, you're going to see, you see the super period here, whose the wavelength varies inversely proportional to the twist angle. So now I'm going to twist it back, and you see the pattern becomes larger and larger because the angle becomes smaller and smaller. And what this pattern, basically this is an interference pattern. The bright spot here corresponds to positions where the top layer atoms are perfectly aligned with the bottom layer. So the top layer atom eclipses the bottom layer atom. We call that AA stacking. The dark regions are ones where the top A atom sits on a bottom B atom, and the top B atoms have no neighbor, and vice versa in the BA region. So this is how we create this Moiré pattern. However, this Moiré pattern does something more than that, than just this pretty interference pattern. And if you calculate the energy to have an AA stacking, you see that it is vastly larger than the energy to have an AB stacking. So as a result, this Moiré pattern induces a modulation in the height of in the spacing between the two layers, which is about a 10% modulation. So you have peaks and valleys alternating that follow the pattern of the Moiré cell. One of the consequences in terms of the density of state is that the electrons will love to pile up in the AA region. So you have a large density of state in the AA region that alternates with small densities of state in the valley regions, in the AB regions. So so let's take this red layer on top of the blue layer, of the green layer, and that causes you have a corresponding stacking of the Moiré-Brillouin zones. And you see that the K value of the green layer is displaced from the K value of the red layer by an amount, by a wave vector, which depends on the twist angle. So the larger the twist angle, the further apart they are. So this little region here is our mini Brillouin zone. We've cut down our Brillouin zone into small pieces, and this is where we're going to be looking for our flat bands. So if I'm looking at the Dirac cones, these two Dirac cones, the green and the red, you see that they meet here at an energy that depends on the twist angle. Now, as long as the two layers don't talk to each other, in other words, as long as there's no tunneling between the layers don't care about each other. However, as soon as tunneling occurs between the layers, you have a hybridization between them, and that gives rise to a saddle point in the band structure, which translates into a singularity, which you call Hove singularity, in the density of states. So these Van Hove singularities are marking the band the bandwidth. So we have a new band, a new mini band now that has shrunk by an amount that corresponds to the twist angle, and its bandwidth is just the distance between the two Van Hove singularities. Let me do a little simulation here. So this is a simulation of the band structure as a function of twist angle, and you see as you reduce the twist angle, the band becomes flatter and flatter and flatter until you reach 1 degree, which we call magic angle, where it's completely flat. And as you continue to decrease the twist angle, it starts swelling up again. So in order to see these effects, we can do scanning tunneling microscopy. Now, what's a scanning tunneling microscopy? Sorry. So bring a sharp tip, metallic tip, to your substrate and apply a voltage between the tip and the sub. Bring it close, but not without touching, and monitor the current that flows in this circuit. So this is going to be a tunneling current. The tunneling current depends on two parameters here. It's the height of the distance of the tip to the substrate, and it depends on the density of state inside the integral here. So that allows us to make two measurements. One is in which we keep the current constant and the bias constant, and we raster the sample and we adjust the height of the tip so that the current is constant. And that gives us an atomically resolved image of the atoms that sit in our substrate. Another mode of operation is one where you're looking at the density of state, and for that you just take the derivative of your current with respect to bias, and here it gives you the density of state. This is an actual measurement, the density of state of a graphene, of a monolayer graphene, and you see it's linear in energies if the horizontal axis. So the density of state is linear in energy. The Dirac point here is the minimum of this of the density of state, and the Fermi energy in these kinds of measurement is always designated as the zero of energy. So here we have a nice separation between the two, between the two energy scales, and depending on what gate voltage we apply, we can move the Fermi energy with respect to the Dirac point. Another thing that we can do is apply a magnetic field, and there you pop up the Landau levels pop up beautifully, and then once you have Landau levels, remember the energy of the Landau level is proportional to the Fermi velocity, to the velocity of these of the electrons in the Dirac cones, and by fitting this curve and by as a function of magnetic field or filling. Or level index, you can extract the Fermi velocities. There are other things that you can extract, like quasi-particle lifetime or coupling to the substrate, which I will not discuss. But the Fermi velocity we will use later in this talk. So here is the first experiment that we did, and here is where serendipity came into the picture. We were trying to measure the properties of a graphene layer, a single graphene layer that was isolated from the substrate, because the substrate introduces a lot of disorder. So at the time, we didn't know how to handle these samples. So this sample was grown by Jing Kong at MIT. She grew it by using chemical vapor deposition of graphene on nickel. And then it was sent to Manchester to Kostya Novoselov, who deposited on this electron microscope grid. Now, if you zoom into the this electron microscope grid, so you see these holes where you have suspended graphene, and here is the gold grid. Here we have a single layer graphene, and then it turns out that inadvertently this was not a monolayer graphene, but it contained many twisted bilayers with any twist angle that you could have imagined. So at the time, we had no idea that this is going to be very interesting, but looking at it, we had many surprises. So we measured one such twisted layer, and you can tell the twist angle just by looking at the period of the Moiré pattern, or you can look at the Fourier or at its Fourier transform, and immediately you can get out the twist angle, and then you look at the density of state. In this case, it looks very much like monolayer graphene, but then when we go to smaller and smaller angles, here we have an angle of 3.5 degrees, suddenly you see these peaks, and as you keep decreasing the twist angle, the peaks keep coming closer and closer together. And eventually you come to a point where the peaks actually merge together. And this is 1.1 degree. This is a twist angle that we call the magic angle. And here the Fermi energy is 0. We have a small gap in the Fermi energy, which is very intriguing because it tells us maybe there are correlation effects that are going on. So this is what we thought at the time, although we couldn't do much more than this. And then we go to a smaller angle, and again, the band becomes wider at this is 0.28 degrees. But because the Moiré period is so large, the AA region now can shrink. So you see this AA region have shrunk dramatically, and they're connected by these one-dimensional channels, which turned out to be very interesting, but I'm not going to go into that today. So plotting the separation between these Van Hove singularity peaks as a function of twist angle, you reach a point, and that was another surprise at the time, where the separation goes to 0. And what this means is that you have a flat band. So that means that your band has become flat here at this magic angle, which is not 0 degrees, but 1.1 degrees. And of course, now the band capacity, this narrow band, can take 8 carriers per Moiré cell, because now we have the degrees of freedom are 2 for spin, 2 for layer, and 2 for valley. So we can, so 8 carriers per Moiré cell will fill this band. Now we can also measure the Fermi velocity, because, okay, when you reach such a flat band, clearly you've kind of stopped the electrons dead in their tracks, and now they can interact, they see each other. So we wanted to measure the velocity, and we managed to measure about 3 points using Landau level spectroscopy. And so we saw about an 80% decrease in the Fermi velocity. We couldn't go any further here. But fitting into theory, this shows that as you go to the magic angle, not surprisingly, the velocity just goes to 0. Okay, so but at the time we couldn't control the twist angle, and we couldn't control the Fermi energy as well. So at this point we were pretty much stuck. And so the field had to wait for another 6 years to get to the next level of control. So this is what happened. This was a team led by Emil Tutuk and at University of Texas, Austin. So here's what they invented. This is a way to manipulate these one atom thick levels by different degrees of stickiness to polymers and to substrate. So here you deposit a layer of graphene the usual way on a silicon dioxide wafer. Then you pick up, by using these two polymers, you pick up a piece of boron nitride. And the boron nitride is critical. This was another advance in the field, because if you encapsulate graphene in boron nitride is a sister material to graphene. It's also honeycomb structure. It has it's roughly the same lattice spacing, but it's an insulator. It's a beautiful crystal, and it can protect graphene from interaction with deleterious random effects, random potential that come from the environment. So encapsulating graphene in boron nitride is really crucial to bring out the intrinsic electronic properties. So you put your boron nitride on top of half of graphene, and it sticks. Graphene likes to stick to it better than to silicon dioxide. You pick up that half, you rip it. Sorry. You pick up that half, you rip it away from its brother, then you align them again, and now you very carefully can change the twist angle between the two, and then you press it down again, and then you do similar things. You can put another layer of boron nitride or whatever, and you can make a device out of this. So the group of Pablo Sharia Herrero at MIT used this technique to make a device, to make a transistor. So here we have the twisted bilayer graphene, and it's nicely encapsulated and protected with boron nitride. You have a source and drain electrodes. You have a gate electrode. So you can change the Fermi energy. You can throw electrons into your sample or pull them out just by the gate voltage, and you can measure its transport properties. And then they took the device, cooled it down to very low temperature with a dilution refrigerator close to absolute zero, and they saw, and this is where the big surprise came. So they saw this phase diagram here. Here we have temperature. Notice how low the temperature is. And here you have number of electrons per unit cell. So they noticed that when you have about -2 electrons is equivalent to -2 is 2 holes. It's equivalent to 2 electrons in the band. So when you have 2 electrons in this 8-electron band, they saw that you have an insulator, and the insulating phase was flanked by 2 superconducting domes. So inside these domes here, the sample went superconducting. And the superconductivity here was pretty pathetic. The critical temperature was below 1 degree Kelvin. So nobody would take this, get excited about it. However, this was a huge excitement. They announced this work at the 2018 March meeting. And this was, all the 10,000 participants were absolutely excited about this. Now, why the excitement? The reason people got very excited about this is by looking side by side at the phase diagram of this twisted bilayer graphene and high temperature superconductor. And there are a couple of similarities. High temperature superconductor, you have an insulating plate flanked by 2 superconducting domes. Another important factor was the critical temperature divided by the Fermi temperature is relatively large. It's similar in both systems, which means that we have strong coupling between the electrons. The glue that holds them together and makes the superconductivity is quite strong. And however, whereas every point on this phase, on the high temperature superconducting phase diagram is requires synthesizing a different sample. So it's extremely painful to generate a phase diagram like this. In the case of twisted graphene, all you have to do, you just change the doping with the sweep of a battery, basically. So this makes getting the plotting out the phase diagram and exploring the physics of this system so much easier. So of course, people then started asking, okay, will this help us solve the decades-long mystery of high temperature superconductivity? First, let's see if there are similar phenomenologies. So just above the superconducting dome, there's a pseudo-gap phase where we have nematic order. We have charge or spin order arranged in stripes. Do we have that here too? Is there a pseudo-gap phase where the gap closes but not quite, the superconducting closes but not quite? Do we have strange metal behavior in this region, which basically means that the resistivity is linear in temperature down all the way to the lowest temperature, telling you that this is the only energy scale in the system. So people started working on answering this question, and there was great hope that maybe it's going to help us. This is a simpler system. Maybe it's going to help us solve the mystery of high temperature superconductivity. So we decided to look at it again. So this time we didn't use chemical vapor deposition graphene. We used exfoliated graphene. We treated it the same way by the tear and stack technique, but we omitted putting the top bore nitride layer on top so that it allowed us to look at the sample with scanning tunneling microscopy, which allowed us to look at the density of states of this system. So here is the topography. This is a sample that is twisted at a magic angle. This is the Moiré pattern, which is about 13 nanometer, has a period of 13 nanometers. And this is a zoom in, so you see the individual atoms in the AA layers and AA regions and AB regions. And next we looked, now that we could gate the system, we put our Fermi energy so that this flat band, we see that this is a flat band now, it's fairly narrow, 40 millivolts. So we could go and search on this sample. We have many twist angles on this sample. We could go and search for the region where the band is narrowest, where the two Van Hove singularities have really merged. And this is where we found it. So now we gate the sample to put the Fermi energy outside of the flat band. So the band is, so this is undoped. And you see we have this nice flat band. Then we gate it and we move the Fermi energy to the other side. The band is pretty much unaffected. And now we're taking the Fermi energy and putting it smack inside the flat band. And look what happens. We're opening a gap. This is a pseudo gap. This is not a full gap. This experiment is done at 4.5 degrees Kelvin. So this is a classic correlation-induced gap. So we call it a pseudo gap because it's really not a full gap. Full gap that would go to zero here. So there are 3 other groups that have seen similar effects from different points of view roughly at the same time. And what we did next is we were asking, is there nematic order here or not? So what we did, we devised a way to actually measure the charge distribution inside the sample. I don't have time to go into how this was done, but we could measure the charge in the system. So you start out with topography. You have a clear, beautiful six-fold symmetry here. These are the AA regions. And now we measure the charge spectroscopy in this region. This is exactly the same region of the sample. And you see that the charge has broken up into the stripes. We have nematic or stripe order or nematic order. So the red lines correspond to 1 electron per Moiré cell. Blue is 1 hole per Moiré cell. And you see how beautiful these alternate. So you really have some charge order that is established there. And this charge order is only when the Fermi energy is within the flat band. As soon as you go outside of the flat band, or as soon as you apply a magnetic field that's above about 8 Tesla, this goes away. So this convinced us that this is an intrinsic rearrangement of the charges of the electrons due to the correlations in this system. So now we can reassess where we are. So yes, we have a pseudo gap phase, just like in high temperature superconductor. We have nematic order as well. Is there strange metal Planckian dissipation? There are experiments now from several groups that seem, and from our group as well, that seem to indicate that even this this marker is similar in both cases. So where are we now? So let's have what's the scorecard? So at this point, it looks like a magic angle twisted bilayer graphene has many similarities with high temperature superconductors, but in fact, it is much richer. And also, it looks like it may not help us solve the mystery of the mechanism of high temperature superconductivity. It's also unlikely that it will bring us to room temperature superconductivity, but there are many, many interesting things there to explore. For example, whereas in high temperature superconductors, we have 2 domes that flank the insulating phase, it turns out that in graphene, we have many domes that they flank each integer filling. In superconductivity, the insulating and superconducting phase are kind of brothers. They go hand in hand, whereas it turns out that in magic angle twisted bilayer graphene, they are inimical to each other. So for example, when you bring your screening gates, you're close to the layer, it really destroys the insulating phases, but superconductivity is left. So it looks like in graphene and twisted graphene, the insulating and superconducting phases compete rather than cooperate. There are many other things that we see. There's orbital magnetism when you have an integer filling of the Moiré cells, 1, 2, 3. At 3, one sees orbital ferromagnetism. There are topological properties. There are churn insulating phases that occur at integer band fillings. And I don't have time to go into this, but many of these things are detailed in these references here. I have, okay, so I think I have time I'm going to run for another maybe 5 minutes to tell you about flat bands that are introduced with strain. So let me start with buccal membranes. So this is known from engineering, actually, from mechanical engineering, that if you have a thin, stiff membrane under biaxial compressive stress, it will buckle. And so there's a critical stress where this membrane will buckle, and it will create a periodic buckling structure, which depends on the stress, depends on the substrate, and depends on the mechanical properties of the Young's modulus of this membrane. So one can get all sorts of beautiful buckling patterns like triangular patterns, stripes, checkerboards, and so on and so forth. So we did that with graphene. This happened accidentally by differential thermal contraction, and we were able to create a buccal graphene structure. So this was a graphene that was actually deposited on niobium diselenide. And again, this was another instance of serendipity. The results that we saw were completely unexpected. So what happened, we created this buccal structure. You see it's a triangular structure. And if you plot the height along this direction here, you see that you have a height modulation of about 1.5 angstroms. So if we do spectroscopy of this layer here, and we go to the crest here, and we look at the density of state maps, you see that this is the triangular structure rather than hexagonal structure, rather than honeycomb. So we only see the atoms in one sublattice. And then when you go to the troughs, you see the atoms in the other sublattice. So that tells us that what we have here is a pseudomagnetic field that is induced by the strain which is present in this buccal structure because of the stress of compression. And then you can go in the intermediate, in the crossover region, in between the two, and there the wave function sits on both sublattices. So we know that we have a pseudomagnetic field here that is strain-induced. So let's now go and look at the density of states and see if we have pseudo-Landau levels here. So here we look at the crest, and we take the spectrum, the DIDV spectrum, density of state as a function of energy or bias voltage, and you see that you have good Landau levels forming. The first one is much higher than the others. And then you can just plot them, plot the energy versus square root of the Landau level index, and that gives you an effective pseudomagnetic field, which is humongous. It's about 108 Tesla. And then you measure the Landau levels, you measure the spectra in these trough regions, and you find that the pseudomagnetic field is about minus 80 Tesla in the troughs. And then you can look at a band structure. This is a theoretical band structure. You indeed have flat bands here, which is what these peaks are telling us. So we have created a system with flat bands. Now, unlike the blister that I showed you before, where the pseudomagnetic field was concentrating in one point and it was not spreading over the entire sample, because we have a periodic structure of pseudomagnetic field of these blisters, that's why we have flat bands that spread out through the entire sample. And here you can see how they propagate along the sample, both experimentally and theoretically. Each one of these bands, you can see their distribution within the sample. Now the buckling transition, we don't have too much control of the buckling pattern that you're going to get. So ideally, you'd want to have some control over it. So we started to do something to try to simulate the buckling, and that is you can create a pattern of pillars here, and here we have gold pillars sitting on top of boron nitride, and then you can cover them with graphene. You put a drop of liquid so that it really sucks into into the substrate here. And what happens if you hold it in place at the edges, you will have huge strain that is building up here. And the strain pattern is whatever you want, depends on on the pattern of your pillars. And also the strength of the strain depends on the aspect ratio of the height of the pillars and the distance between them. So here is what we get. This is our scanning electron microscope image of this sample. So this is graphene on top of the gold pillars. The distance between pillars is about 2 microns. And you see that, of course, because you have these pillars, just because of the topology, you must, and you're trying to project in 2 dimensions, you must create folds that connects all these pillars. And you see this beautiful network of folds that connect them. So now we go into one of these regions here and we measure the density of states, the spectroscopy. And lo and behold, we see beautiful Landau levels appearing. Again, just as before, we can fit the sequence of energy to square root of the Landau level index, and we get a magnetic field which is kind of low, but this is a function of the geometry of this pattern. But we can induce a pseudomagnetic field of about 8 Tesla. So this gives us a pathway to continue to get much higher pseudomagnetic field and to eventually get flat bands and possibly correlation-induced phases, correlated phases. And this brings me to the summary. So I covered we had three ways of creating flat bands in this case, all of them involving graphene. So first we started out with, overlaying 2 layers of graphene or any kind of crystals will give you a Moiré pattern, which gives rise to Van Hove singularities when you have hybridization between the 2 layers. At a magic angle of about 1 degree, you get a flat band. And that gives rise to various very interesting correlated phases when you bring the Fermi energy into these bands, especially when you have integer fillings of the Moiré cell, superconducting domes, and we see a precursor to superconductivity, which is a pseudo gap and the nematic order. Now, when we are able to put the graphene on an array of pillars, which enabled controlled stretching of the system and controlled application of strain, and that gave rise to a pseudomagnetic field. And the same thing happens when you have naturally buckled graphene, where we see pseudomagnetic field that can be as high as 100 Tesla and giving rise to flat bands without breaking time reversal symmetry. And okay, so the most important part of this talk are the people who actually did the work. So here are the people, the Rutgers researchers that did the graphene postdocs and students. In red here we have our Japanese collaborators who supplied the boron nitride. Andrei Gaim and Yang Kao supplied the niobium diselenide, the sample that buckled. And here we have the team, the Belgian team that did the theory for the buckled graphene, and Christian Haule from Rutgers, who helped us with theory for the magic angle twisted graphene. So of course, we just scratched the surface of this field. It's a huge field with lots of interesting possibilities, but also with lots and lots of challenges. So we have experimental challenges. We need these twisted bilayers are extremely inhomogeneous. They're strained. There is defects that are included, and one has to, the sample homogeneity is a big problem. And maybe with more homogeneous sample, it might be possible to increase the superconducting temperature. Right now, the record is about 3.5 degrees Kelvin above absolute zero. So we have a long way to go. We'd like to actually get direct access to the band structure by doing angular resolve photoemission. We'd like to have magnetic probes to probe the magnetism of these layers when they're partially filled, measure thermal conductivity to get some idea about the coupling in the superconducting phase. Many theoretical open questions like what is the pairing mechanism? What are the broken symmetries that give rise to these new phases? Can our understanding of this system shed some light on the high temperature superconductors, and how high can we push TC of superconductivity? Can we get to room temperature superconductivity? So ideally, we'd be looking for more robust systems, such as artificially strained membranes. And of course, there's a huge, vast arena of different kinds of two-dimensional materials, which are begging to be explored. And thank you for your attention.